Next, we'll discuss an application of the decomposition principle to solving two-stage stochastic linear programs with fixed recourse. So we consider a situation when the decision maker has to act in two stages. The first stage involves choosing or implementing decision vector x, and then one out of k possible scenarios realizes. So we saw in the farming example that the first stage decision was to determine how many acres of land to allocate for different crops. And then once that decision was made, we had to wait and see which of the three weather scenarios will materialize. So we assume that the probability of scenario omega is given by alpha omega, and that probability is positive. As an example, in our farming model, we assumed that each of the three scenarios was equally probable, so all three alpha omegas were equal to 1/3. So we make the first stage decision given by the vector x, and then we wait and see which of the k capital scenarios are going to realize. Once we know that a scenario omega realizes, we react by implementing the decision y omega. So this is our second stage decision variable. And that second stage decision variable depends on the scenario omega. So in our farming example, the second stage decision variables were y's and p's, the amounts of crops that we are going to buy and sell. Here in this description, we denote all the second stage variables by y omegas. Next, we discuss the objective function. We are given cost vectors c and f for the first and second stage decision variables respectively. In particular, the first part of the objective function will be c transposed x, so this is the cost corresponding to the first stage decision, and in our farming example that was given by the planting cost. And then for the second stage, we have the expectation of the cost for the second stage decision. So this was given by the summation of alpha omegas multiplied by f transposed times y omega. So we are optimizing the expectation of this sum of two costs for the first stage and the second stage, but the actual second stage cost that will be realized is not known until we know the realization of the scenario omega, at which point we just compute f transposed times y omega for that particular omega, and that will be our actual cost that we will encounter in practice. Again, I want to reiterate that the optimal objective value for the stochastic linear program just gives us the expected cost per year or per period on a long run, and we will never really encounter that exact cost in any particular year. Finally, we have two types of constraints in our model. The first stage decisions must satisfy the first set of constraints given by ax is equal to b and x is non-negative. In our farming example, this part corresponded to the constraint on the total amount of land that we have. So recall that it was x1 plus x2 plus x3 is less than or equal to 500. And for the second stage decision variables, together with the first stage, we have another set of constraints given by b omega times x plus d times y omega equals to d omega. So here b omega is the part of the constraint matrix corresponding to the x variables, then d matrix is the fixed recourse matrix. So this part corresponds to the second stage decision variables in the constraints, and this actually gives the name to our problem. So this is a two-stage stochastic LP with fixed recourse. Why with fixed recourse? Because the second stage decisions represent what we call the recourse actions that we implement after observing the outcome for the stochastic scenario. And this matrix D corresponding to the recourse variables is a constant matrix. It doesn't depend on the scenario. That's why this is a problem with fixed recourse. In our farming example, the yield of each type of crops depended on which scenario realizes, and this is represented by this matrix B omega in our general description of the model. And then in the example that we considered, the right-hand sides didn't really depend on the scenario, but this framework that we are discussing allows to have the right-hand sides, such as the demand for cattle feed, for example, depend on this scenario. Now we are ready to formulate our general model. So we have the objective of minimizing C transposed X plus the summation for omegas between 1 and k capital of alpha omega times F transpose times Y omega. This is the first stage cost. This is the expected second stage cost. And then we have the constraint for the first stage given by AX is equal to B. And we have the constraints involving both first and second stage variables given by B omega X plus D times Y omega is equal to D omega. And these constraints are specified for every scenario. And finally, we have the non-negativity of all the variables. If we expand this formulation, here is how it is going to look like. So we have a clearly defined block structure in this problem. So in the first set of constraints, we only have the X variables with the coefficients given by this matrix A. Then the first scenario has matrix B1 corresponding to the X variables, and then it has the matrix D corresponding to the second stage variables written for the first scenario. Then for the second scenario, again, we have matrix B2 of the same size as the matrix B1, and exactly the same recourse matrix D for the second stage variables corresponding to the second scenario. Then similarly for the third scenario, we have matrix B3 here and D here. And finally for the last scenario, we have BK here, D corresponding to YK. And actually, if we look at this structure, we see that removing the part corresponding to the first stage variables, we have this block diagonal structure to our problem. And in fact, if I connect these blocks corresponding to the same row, we have this L-shaped structure, as we call it. So there are these L's that we can observe in the structure of this problem. So the biggest one would be if I look at the last scenario. So we have this L here. So this is what we call the L-shaped structure. Now, if we look at the dual of this problem, then the blocks of the constraints will correspond to these columns right here. So we'll have the block corresponding to the X variables, then the block corresponding to Y1 columns, then the block for Y2 columns, and so on. Finally, the block corresponding to the YK columns. Then looking at the dual, we can see that there will be a block of constraints involving pretty much all the dual variables, but then the remaining blocks of constraints will have the block diagonal structure. And we already know that these type of problems are suitable for solving with Danzig-Wolff decomposition, and this is what we are going to do to solve our stochastic LP. So essentially we are going to look at the dual of this problem and we will solve it using the Danzig-Wolff decomposition. since we are switching to the dual, what used to be the variables now corresponds to the constraints, and instead of the columns, we will be generating the rows when we look at the primal problem. So applying the Danzig-Wolf decomposition framework to the dual problem becomes what we call the Bender's decomposition for the primal problem. And in this case, we will be generating the constraints instead of generating the columns. So let's consider this two-stage stochastic linear program with fixed recourse and assume that we are given x, the first stage decision variable satisfying the constraint ax is equal to b. Then we can determine the optimal values for the second stage variables for every scenario by solving the following LP. So let's denote by z omega the minimum of f transposed times y omega, subject to we have dy omega is equal to d omega and then minus b omega times x. And of course y omega is non-negative. And we can write down this LP for every omega between 1 and k. And of course the optimal objective value here depends on x, so maybe let's make it more explicit and let's use the notation z omega of x here. Let's denote this LP by s omega, so this is our scenario problem. And of course, we want this problem to be feasible in order for our stochastic LP to be feasible. But then if it is not for some x, then we will set the corresponding value here to plus infinity. So essentially, if s omega is infeasible, then we have z omega of x is equal to infinity. Then we can rewrite our LP as follows. Minimize C transposed x plus the summation for omega between 1 and k capital alpha omega times z omega of x, subject to ax equals b, and then x is non-negative, where of course z omega of x is the solution to this LP right here. Now let's consider the dual of the scenario problem here. Let's denote the dual variables by p omega. Then our dual LP is going to be maximize d omega minus b omega x transposed multiplied by p omega, subject to d transposed p omega is less than or equal to f. Now note that the feasible region of the dual LPs for different scenarios is actually the same, and only the objective differs from one problem to another. So let's denote this feasible set, which is common for all the dual problems for each scenario, by p capital. So and this will be the set of p's such that d transposed p is less than or equal to f. And it is reasonable to assume that this set is non-empty. And also let's denote by pi's for i between 1 and r the extreme points of this set P. So we assume that there are r extreme points, and then we'll also denote by wj's for j between 1 and q the extreme directions of P. So we assume that there are q extreme directions. Now, since we assumed that P is non-empty, this problem here will be infeasible if and only if the dual is unbounded, right? So we have z omega of x is less than infinity if and only if the scenario dual is bounded, which means that for every extreme direction of P, we need to have the objective value that is non-positive. So we have d omega minus b omega x transposed multiplied by any extreme direction wj must be less than or equal to 0 for any j between 1 and q. This is if and only if condition, right? So whenever this holds, this means that the problem is bounded, so it's feasible and bounded, so it's going to be optimal, and in this case z omega of x is going to be equal to the optimal objective value of the scenario dual. On the other hand, if there is a wj for which this product is greater than 0, then the scenario dual is going to be unbounded, so the primal is going to be infeasible, meaning that z omega of x will be infinity. So if z omega of x is finite, then the optimal objective value for the dual will be achieved at one of the extreme points of the set P, and our z omega of x by strong duality will be equal to the best objective value for our dual at an extreme point of the set P. So here I'll write Pi, the extreme point of the set P, and we take the maximum over I between 1 and R. So whenever z omega of x is finite, we can find it by finding the best extreme point of the feasible region for the scenario dual. Finding this maximum is equivalent to finding the smallest value of z omega that is an upper bound on all products like this for I between 1 and R. So this is equivalent to finding z omega that would be greater than or equal to d omega minus b omega x transposed multiplied by pi for all I between 1 and R, and we want to find the smallest z omega that satisfies each of these inequalities here, and this will give us z omega of x, right? Therefore, now we can reformulate our problem given here as follows, and this is what we call the Bender's reformulation. We want to minimize c transposed x plus the summation of alpha omegas z omegas. Now z omega is this variable that we introduce here, and since it is in the minimization objective together with positive multipliers alpha omegas, we ensure that we look for the minimum z omega that will satisfy each of these constraints. Therefore, we will indeed find the z omega of x, right? So here omega is between 1 and k. And then the constraints are subject to ax is equal to b. So we have this constraint right here. We'll keep the non-negativity of x for later. But now we need to specify the remaining constraints. The first set will ensure that we have the bounded scenario dual, and it's given by d omega minus b omega x transposed multiplied by wj is less than or equal to 0 for j equal to 1 through q. And now we need to put this in for every scenario omega, right? So omega is between 1 and k. And then we specify the constraint for z omega. So we have this inequality. We will write it as follows: d omega minus b omega x transposed times pi is less than or equal to z omega for I between 1 and R, and for omega between 1 and k capital. And finally we have the non-negativity of x. This is our Bender's reformulation. And solving this reformulation is equivalent to solving the original LP. If we look at what advantages we gain compared to the original LP, now we have a lot fewer variables, right? So for each scenario, we only have one variable z omega, but the number of constraints that we have here, look, we need to have a constraint for every extreme direction and every scenario from this set, and every extreme point and every scenario from this set. So the number of constraints can be huge. Therefore, instead of spelling out the whole Bender's reformulation, we will only specify a few of these constraints and then generate the remaining ones that are necessary as we need them. So essentially we are going to drop most of these constraints, and as a result we will obtain a relaxed problem, because whenever we drop constraints we relax our feasible region, and this resulting problem we will call it the relaxed master problem. So the relaxed master problem, RMP, recall that in Danzig-Wolff decomposition RMP stood for the restricted master problem, and here we are talking about relaxed master problem. So here is how we proceed with the iterations of Bender's decomposition. So assume that we solved the relaxed master problem and we obtain the solution given by x star and z omega star. So this is the optimal solution to the current relaxed master problem. Then we need to verify if this optimal solution to the relaxed master problem is in fact optimal for the whole master problem here. For that we need to make sure that all the constraints that we dropped are satisfied by this point x star z omega star, or if they're not all satisfied, then we need to find the constraints that are violated and add at least one violated constraint to our relaxed master problem, and then resolve the relaxed master problem and proceed this way until we can guarantee that all the constraints are satisfied by the solution to the relaxed master problem. So to verify if x star z omega star indeed satisfies all the constraints in the master problem, we need to solve what we call the separation problem. The separation problem checks whether a given point belongs to the polyhedral set, and if it doesn't belong to the polyhedral set, then it finds a constraint that is violated. This constraint is the one that separates our point from the set, so that's why it is the separation problem. And for us to solve the separation problem, we need to solve the scenario dual for every scenario, right? So we are solving this problem right here, and as a result of solving this problem, we either produce the unboundedness, in which case we are going to generate a direction that will violate this constraint here, so we'll have greater than 0 for the given direction. And if this is the case, we are going to add this constraint for the extreme direction that we produced. Otherwise, if the problem is bounded, we are going to obtain an optimal solution to this problem at an extreme point. And then for that optimal solution given by Pi, we are going to check if the corresponding constraint here is satisfied with x equal to x star and z omega equal to z omega star. If it is satisfied for every scenario, then we conclude that this optimal solution to the relaxed master problem is also optimal to the master problem, and we are done. Otherwise, we will generate a new constraint of this type and we will move on to the new version of the relaxed master problem with an additional constraint, and we keep going until we terminate. The process is summarized here. It is also referred to as delayed constraint generation. So we start with the relaxed master problem, which is the Bender's reformulation with only a subset of the constraints instead of all the constraints. And then we solve the relaxed master problem to optimality and obtain the optimal solution X star Z star to the relaxed master problem. Then we need to answer the question if it is feasible for the Bender's reformulation, which is our whole master problem. And for that we solve the separation problem by solving the scenario dual for every scenario. It was given by maximizing this objective function subject to the constraint given by this polyhedral set P. As a result of solving this problem, we either obtain the unboundedness, in which case we find an extreme direction Wj such that one of the constraints of the Bender's reformulation is violated, and we are going to add the constraint with this given by less than or equal to 0, and we update the relaxed master problem with this constraint and then proceed to the new iteration of the method. Or if the scenario dual is optimal, we are going to find an extreme point Pi that is optimal, and again, if we are violating one of the constraints of the Bender's reformulation, then we are going to generate a new constraint like this, and we'll update our relaxed master problem and proceed to the new iteration. And finally, if for all omega the scenario dual is optimal and the optimal solution satisfies this constraint, then no violated constraints exist and our solution to the relaxed master problem is indeed optimal to the Bender's reformulation, meaning that it is optimal to the original stochastic linear program.